Hello everyone, this is Amog Rao. I am a graduate student at University of Florida under the Electronics and Computer Engineering department, and this is my submission for the course EEL6825 pattern recognition. Basically, this is a project based on a comparative study and analysis of background subtraction techniques. Okay, the background subtraction technique, also known as foreground detection, is a technique widely used in image processing and computer vision. The critical primary step in many of the computer vision applications is processing the video stream to detect the foreground objects from the background. The background subtraction approach identifies moving objects from the video frame by distinguishing the pixels that differ significantly from the background model. There are a number of challenges faced while developing such an algorithm. They are: firstly, it is how robust it is under the circumstances of illumination. Second is to avoid detecting any non-stationary background objects, and also avoiding the shadow detection of the moving objects. This shows a simple flow diagram of the four major stages in a background subtraction technique, which involves pre-processing, background modeling, foreground detection, and data validation. Let's go through these stages one by one. The first stage is pre-processing. Basically, it is used to reduce the camera noise by using temporal and spatial smoothing. Smoothing also helps to remove noise effects due to the environmental conditions like rain, snow in an outdoor camera, which causes many inefficiencies. But for real-time systems, techniques are used for frame size and frame rate reduction for data processing rate reduction. Another issue to take care in pre-processing is the format of data used, as it would affect the memory requirements, and hence it would affect the performance rate of processing. Many of these algorithms use luminance intensity, which is just a single value per pixel, making it attractive, but it may affect the accuracy. However, to improve accuracy, people also use RGB or HSV, that is a color-based image, because of its performance advantages at low contrast, and also for suppressing shadow casted, which causes noise. But the drawback of using color or any spatial temporal derived features is that it adds additional complexity to compute the estimation of the model parameters. This increase of complexity is quite significant because most of the background subtraction models have an independent model used for individual pixels. Second stage is the background modeling. The background model should be robust against any kind of changes in the background environment, and also should be sensitive such that it should be able to identify moving objects efficiently. So the background modeling techniques are classified as recursive and non-recursive. Non-recursive technique. In this kind of approach, the background estimation is done using a sliding window buffer, which stores previous n video frames, and an estimation of the background is done using temporal variation of each of the pixels which are present within the buffer. These techniques do not use any of the history beyond the ones stored in the buffer, which makes them highly adaptive. But if a large buffer is used, then the storage needs become quite significant. On the other hand, recursive technique performs a recursive background model update based on each input frame instead of using a buffer of frames for background estimation like it is in non-recursive technique. Thus, these techniques consider effects of frames from the distant past on the current background model. They have low storage and hence have memory advantages, but also if any error persists, then it will linger for a long time in the model and is going to take a long time to exit the model because it is dependent on the history. Generally, exponential weighting is used to rebate the past and use only positive feedback for performing updating using only the background pixels. These are some of the non-recursive techniques: frame differencing, mean filter and median filter. Frame differencing, this is a basic form of background subtraction technique in which the consecutive frames are compared and the difference is calculated for each pixel. And if this difference value after the subtraction crosses a threshold value, then it is classified as a part of the foreground. However, as it only uses the previous frame, it may be incapable of tracking and identifying the interior pixels for a large moving object, and this causes the aperture problem. Next technique is mean filter technique, in which the thresholding is compared with the mean of all the frames at each pixel presently stored in the buffer. Similarly, the median filter technique. In this technique, the background is estimated by using the median of all the frames at each pixel presently stored in the buffer. It is modeled under the assumption that the pixel retains in the background for approximately more than half the number of frames. The computational complexity for this algorithm is n log n per pixel. These are some of the recursive technique algorithms, namely KNearest neighbor algorithm, mixture of Gaussians, and GMG algorithm. We'll go through these algorithms one by one. KNearest neighbor algorithm is a background subtraction algorithm which is a non-parametric method used in pattern recognition for classification and regression. It is a type of lazy learning where local approximation of function is performed and the computation is delayed until classification. The neighbors are chosen from a set of objects for which the class or object property value is known, and it is assigned weights to contribution of the neighbors by using the distance of the pixel from the neighbor. Thus, the nearer neighbors will have more contribution towards the average compared to the distant ones. The next algorithm is very popular because it uses the mixture of Gaussians technique. Basically, in this method, each pixel is modeled as a mixture of Gaussians, and it works assuming that every pixel's intensity value can be modeled using Gaussian mixture model. Basically, it uses heuristics to determine which intensities belong to the background, and hence the remaining pixels are declared as foreground pixels. And an adaptive backgrounding method is simply averaging the incoming images over time, thus creating a background model estimation related to the static scene, except where there is a change in the pixel. Basically, it means where the motion occurs. The emoji technique ensures simultaneous storage of multiple Gaussian distributions. It maintains a density function per pixel, making it adept for handling multi-model background distribution. Emoji being parametric, it can be updated in an adaptive fashion without the need for large storage buffer. The mixture of Gaussians that correspond to the background colors is determined based on the variance and also on the persistence of each of the Gaussians. The remaining pixel values that are not included in the background distribution are reflected as the foreground until there is a Gaussian including them. Then the Gaussians need to be updated and the pixel values that do not match any of the background Gaussians are then congregated. The next algorithm is GMG algorithm. Basically, this algorithm was proposed in the paper visual tracking of human visitors under variable lighting conditions for a responsive audio art installation in 2012. And basically this algorithm is a combination of per pixel Bayesian segmentation technique and the statistical background image estimation. In this technique, it considers first few frames for background modeling to employ foreground segmentation algorithm for detection of the possible foreground objects by the use of the method of Bayesian inference. It performs several morphological opening and closing operations for filtering the unwanted noise. It uses an adaptive approach for estimation, as in the newer observations have higher weightage over the older observations for accommodating the variations in illumination. The third step in the background subtraction technique is the foreground detection. Basically, in this phase, the input stream of video frame is compared with the background model one by one, and the candidate foreground pixels are identified from the incoming frame. The common approach for foreground detection is checking if there is a significant variance in the input pixel from the corresponding pixel in the background estimate. This basically shows the differencing and comparison to the threshold. Another way to threshold is by normalized statistics, like shown here, wherein sigma d is the standard deviation and mu d is the mean for all the possible locations. And the third technique for thresholding can be by using the relative difference to highlight in dark areas, like shadows. But this mentioned technique cannot be used when bright images are used, as it won't help to enhance the contrast in such cases. The next and the final stage in the background subtraction technique is the data validation phase. In this phase, using information from outside the background model, the candidate foreground mask is improved. Because the background model has a number of limitations which needs to be taken care of after foreground detection. Few of these limitations are that any connection between neighboring pixels are ignored in the background model. Another limitation is that the pace at which the model adaptation happens may not be sufficient to map the speed of the objects in the motion. And also, lastly, the noise due to the non-stationary pixels may be because of shadow or any moving leaves in the background in general. Basically, it is mistaken as a true foreground object, and all these limitations need to be taken care of in this phase. So basically, the above addressed problems are solved in the data validation step using various techniques like morphological filtering on the foreground mask, thus taking care of all the unwanted false foreground detected objects. Let's go through the demonstration. As we can see, this is a CCTV footage which has been used for this demonstration, and this is the original frame. This one is using MOG, GMG and KNN, and we can see that the MOG and KNN are successful in detecting the motion compared to GMG, but MOG has a number of noises in the background. But we can see in KNN it gets rid of all the unwanted noises in the background and just detects the major moving object or person. And this is basically a snapshot of the evaluation, in which we can see that KNN has the minimum amount of noise in the background. Basically, on the evaluation, I conclude that on performing intensive analysis on each of these algorithms have optimum configuration at which they perform best, because the evaluation was done by varying the length of the history, the number of mixtures, the threshold, the distance threshold in case of KNN, and the learning rate of the algorithm. And we found that emoji algorithm is not very good under elimination conditions. But on comparing these methods individually, we can say that KNN algorithm performs better than the other ones. The advantage of KNN algorithm is also that it is non-parametric, which helps in the storage advantages, because it has low memory needs and low computational cost compared to others, which is very expensive, and has good performance. Background subtraction has a number of applications as listed over here, like video surveillance or traffic surveillance, also for optical motion capture and rising field human computer interaction. So this was my submission for the course pattern recognition. I hope you guys like the project. Thank you.